Hello, YouTube. Nick Herring from Red Label Productions here with you today to present the first in our series of pre-recorded webinars covering audio topics for event professionals. Our goal with these videos is to skip many of the beginner topics which are covered in depth across a number of videos and dive into some of the more intermediate and advanced topics. In today's video, we'll be going over some of the different types and uses of wireless systems, some common features to look out for, as well as some best practices for usage and deployment. So with that, let's get into the deck and get this going. So first, I want to define what a wireless system is. Wireless refers to the link between a transmitter and a receiver, which does not have a cable. So you think about it in the sense of a microphone system, right? Traditionally, you'll have a handheld microphone with an XLR cable run, which is going to go into your console, a preamp in your console, or a recording system, depending on what your system is and your usage is. In a wireless system, that cable is replaced with a wireless link, with basically a radio link, which allows the microphone, which serves as a transmitter, to transmit and broadcast a signal over to a receiver, which then takes it and then runs into the console there. In wireless systems, there are still wires. You do still need a cable to run between the receiver and the console, and there is still going to be a power cable with this. Every once in a while I'm speccing out wireless systems for customers, I do get a fair amount of surprise when they go, hey, there's still wires with this. And yes, there is. Unfortunately, it's not something that we just don't use at all. It's something that we definitely need. We just have. It's just the long run is going to be done without that wireless, without that cable there. So as we just mentioned, the transmitter is the device that broadcasts the wireless signal. In microphone systems, it's generally going to be a handheld microphone or a belt pack, as we see in the image here. In IEM systems, the transmitter is actually the rack mount unit. It's important to note that when you're talking about microphone systems and when you're talking about IEM systems, they're actually opposite each other. So in a microphone system, the belt pack is the transmitter. In an IEM system, the belt pack is the receiver. So that's something to keep in mind. The receiver is effectively a radio that accepts a wireless signal and decodes it as an audio output. As I just mentioned in the example before, in an IEM system, your belt pack is going to be the receiver. It receives the signal and then broadcast, and then it has an analog audio output out of there. Definitely important to know. Here's some other things that we want to define before we really get into this. First thing we want to talk about is your carrier frequency. And your carrier frequency is basically the main frequency which carries the radio signal. Effectively, it's which station you're tuned to. This is important to note that as we get into this and we start talking about coordination, we'll talk about that in the next video here. We talk about which frequency, which channel are we tuned to. We're referring to the carrier frequency there. That's important to note. Next thing we want to define is our frequency bandwidth and our operating ranges. Frequency bandwidth, basically with that, each wireless system is set to operate over a fixed set of channels. That refers to as your operating bandwidth. It's definitely important to note as you're selecting and speccing out systems. It's important to know what frequency bandwidth you're going to be covering and then what existing interference is going to be there. Existing interference can take place in many forms, from other wireless systems that are being used in your facility to broadcast television stations to public safety radios to all sorts of stuff. You name it, we're competing over the same frequency space. So it's definitely something that we want to keep in mind. The next thing we want to talk about is frequency agility. This is important, and this is an important feature to note while you're speccing out wireless systems. On the lower end, without naming any manufacturers, there are a handful of wireless microphone systems that are designed and intended for prosumer uses, basement karaoke, that sort of thing. They're fixed frequency, which effectively means that if you experience interference on a channel, there's no way for you to change channels and get around it. So basically, if you're tuned to 534.600 or whatever, that's what you're going to be stuck with. And if you have interference on that channel and you experience dropouts and that sort of thing, unfortunately, you're just out of luck. So one feature, one of the biggest features that I point out is you definitely want to look for a system that is frequency agile or has frequency agility. You're able to change and select which frequency you're going to tune to. The next thing we want to talk about and the next feature to look out for are diversity receivers. And basically what that is it's a receiver which utilizes two separate antennas or antenna systems to select the best channel in the case of interference. And so basically if you are paying attention to a diversity receiver system, what will end up happening is you'll notice an indicator LED usually over antenna A, antenna B, and you'll see it flick back and forth. What's happening there is the receiver is selecting which of the two antenna has the stronger and the better signal. When you set up diversity systems, and we'll talk about this more in the next video when we talk about deployment and operation there, it's important to note that symmetry is not required in terms of either the antenna or the cable runs. So it's absolutely a-okay to have a dipole antenna on one side and a helical on the other side, or a fin on the other side, have a long cable run on one side and a little bit shorter cable run on the other side. We're going to talk more about placement a little bit later on, but this is definitely something that we want to note. But the biggest point right now that I want to cover is diversity receivers and what that is. And diversity, to be a diversity receiver, effectively means that you have two antenna and there's circuitry in the receiver that's selecting the stronger of the two antenna, which signal you're going to use from there. So that's important to note. Here's a picture of a diversity receiver. You'll notice the two antenna on the unit itself. Always good to know. Some other features we want to look at, and as we get into some of the higher end features, the higher end systems, we start to notice some features in terms of networking and that sort of thing. As I talk about in the next video, frequency coordination. I personally use Shure wireless, Shure systems throughout all my wireless. We'll talk through wireless workbench. All of that comes together with networking. And so as we get more advanced, we definitely are looking at what we've got in terms of networking ability. Basically, as we move up in these product lines, the more advanced models are going to feature better hardware control. They're going to feature better monitoring. They're going to feature better options for frequency coordination and that sort of thing. So in terms of networking, that's really what we're getting into. As we move up into different systems as well, we move up within product lines. And I talk in terms relative to Shure. And that's just a personal thing for me. I know them the best. All of my equipment is Shure over the course of my career. 85% of the wireless deployments I've done have used Shure hardware. That's not to say that Sennheiser, Audio-Technica, AKG, all those other companies don't make great products. They do. They really do. Just for me, Shure is just a familiar brand. And so that's really what I'll talk in relative terms to as we go through this and we talk through the different product lines and different features to look out for. So as we're looking at this and we look at some features of the different systems and what we're paying for, first and foremost, what you're paying for is the quality of your radio components. And basically what this is referring to is how narrow you're able to make your broadcast bandwidth, which allows you to squeeze your microphone signals in between any other signals or interference which you may have. This is an important feature to note too when we start talking about the differences between analog and digital transmission. We'll talk about that a little bit later on. As you broadcast a signal, you've got a peak on your spectrum analyzer, basically, and the width of that peak determines how much bandwidth you're actually taking up. So even though we say that a wireless system, may be set up at 509.575 megahertz. The reality is that signal is probably going from 508 to 510 or something along those lines. So that's definitely something that we want to note. As you get into these higher systems, basically your receivers become much more selective, and that bandwidth for your broadcast signal actually shrinks. So that's something that we want to take into account. Next thing we want to note is the system frequency agile. I know that we talk about this early on. Across Shure's product line, I believe as soon as you hit a BLX, so basically from entry level on up, really you're in diversity receiver land. The places where you don't get it is when you're in some of the less well-known brands that are making products, as I mentioned earlier, geared for prosumers, basement karaoke, that sort of thing. Not something that we would want to use in any sort of professional application, anything where any robustness of your wireless link is required. Next thing we look at is the system 2.4 gigahertz digital. This is something that we've seen very recently. We see like a Shure GLX or Sennheiser there. I believe EWG3 series is in the 2.4 gig band. Don't quote me on that. I'd have to look it up. But is the system broadcasting there, or are we broadcasting at a different bandwidth? On the lower end of Shure's line, you go BLX, which is analog transmission, generally operating in the same ranges as like a QLX ULS system. Next step up is the GLX system, which is broadcasting in that 2.4 gig band. These systems are very easy to use. Generally speaking, at the price point, they've got advanced monitoring features. As I mentioned, for the price point, the monitoring features on a GLX are very far behind, say, like an Axient system. So I'm not trying to compare the two here, but just saying at that price point, that's something that's very common. The other thing that's important to note about them is because they broadcast in the 2.4 gig band, you're able to use them worldwide without any need for special licensing. So if you're going to be doing an international tour or something along those lines, you don't have to worry about getting into a new country and having the frequency space that your wireless system takes up be illegal in that setting. That happens from time to time. It's something that is important to note. So that's definitely a benefit of these 2.4 gig systems. The trade-off, though, is you're competing with Wi-Fi, you're competing with a lot of cell phone signals, you're competing depending on the carrier and that sort of thing. There's a lot of devices that operate in that 2.4 gig bandwidth. So especially in more urban areas, you may find yourself having a difficult time finding coverage, finding available channels while you set up your system. As I mentioned previously, too, as you move up within product lines, you definitely get into more advanced networking features. I'd mentioned previously the ability to monitor your systems, do network frequency coordination. You can do Dante distribution on a handful of systems. So that's definitely something that's handy, especially as you do bigger deployments, bigger installations, that sort of thing. Also, as you move up within the lines, you gain more hardware control from the apps. And then as you get into the top of the line, the top of Shure's line into the Axient line with ShowLink and that kind of stuff, you can actually then go in and remotely change channels on your systems, change channel on your transmitter while it's in your performer's hand. And, you get all sorts of alerts for low batteries and all sorts of crazy stuff that can be going on, which can be really helpful in your higher profile, higher stakes gigs and events. So that's definitely something that we want to, definitely something to look into when you get to that point. Next thing we want to talk about is analog and digital transmission methods. Generally speaking, wireless microphones in 2020 are all utilize FM transmission, frequency modulation transmission. Basically, just like, we can talk about analog and digital music reproduction and the nuances of that. A lot of that theory translates into this, into the application for FM transmission. And so basically what the differences between the two are, with analog FM broadcast, you're broadcasting an analog audio signal. As such, as your waveform changes, the broadcast waveform actually changes as well. And so, as I mentioned earlier, while we were talking about how selective and how narrow a bandwidth you can broadcast over, with analog FM transmission, that bandwidth actually modulates based on the program material. And so that can be challenging. Say if you're butting up against, say, a TV station, or you're butting up against another channel that you're using, and you've got a signal that's modulating very heavily, that can create problems for you in terms of distortion and the effects that take place with that. In terms of digital transmission, basically what's going on with this is we take our analog audio signal, we go to a A to D converter. Instead of transmitting a sine wave, now we're sending data packets, and we're sending ones and zeros over the broadcast signal. This provides a number of benefits for us, ranging from audio quality to reduced intermodulation effects. And I want to get into intermodulation and what exactly that is here in just a second. But basically with this, because we're sending data packets instead of an analog audio signal, we operate the full bandwidth of our carrier frequency when we do so. So that, because of that, what ends up happening is when you get into a deployment situation, you're much more able to better predict what type of interactions you're going to have, especially if you've got a tight deployment where you've got multiple frequencies close to each other. So that's definitely something that we want to take into account here. We had mentioned intermodulation earlier. Intermodulation is when transmitters that are close in frequency are placed in close proximity to each other. As a result, the radio signals combine and create additional interference. And so if you're looking at a spectrum analyzer and you're looking at this, and we'll show more of this next in the next video here once we get into deployments and that sort of thing, and we're doing some actual readouts. But basically what'll happen is you'll see your two peaks for your two main channels that you're using, and then as you bring those transmitters closer and closer together, you're going to see other spurious signals show up on your system analyzer there, and that creates all sorts of problems for interference and issues that you can have while you're trying to do deployments. And so this is the kind of thing where if you're doing an event where you've got two channels of wireless set up and that's all that you need, you're probably not going to notice this. You're probably not going to need to take the time and figure out what's going on. Do I need to do a full coordination, full deployment, where I need to be concerned about intermodulation? When you're doing, 15, 20 channels of wireless for a big performance and you've got backup channels and all of that sort of thing, intermodulation absolutely comes into play, especially as the frequency space, the bandwidth that we've got to work in terms of our broadcasting, shrinks and gets smaller and smaller and smaller, and is ever evolving. One thing I haven't mentioned up until this point yet is the 600 megahertz auction, which took place recently. Basically, the 600 meg band was a frequency space where wireless microphones were allowed to operate. Recently, within the last year or so, that frequency space was actually auctioned off. T-Mobile purchased it, and now is broadcasting 5G transmissions in that frequency space. The result was that television stations which were broadcasting in that space, and then all of the devices which were broadcasting in that frequency space, all had to move around, all had to get reallocated. And what ended up happening was everybody's competing for less and less space. They're competing for smaller pieces of the pie while all of this bandwidth gets sold off. So it's definitely something that we want to be aware of. Definitely something that we want to acknowledge. Just something that we want to be cognizant of as we get into higher profile, higher stakes gigs with higher density or RF deployments. Other thing I want to point out with our digital systems as we get off into that tangent there, digital systems are less susceptible to RF noise. We're less susceptible to high frequency losses. The other thing that digital systems, the other feature that digital systems offer, which is really nice, is encryption. And basically what that allows is if you're in a situation where sensitive topics are being discussed during your presentations and outside of your event space, we don't want anyone hearing that information. We're actually able to encrypt the broadcast signal. So not only do we have to have a receiver from the same manufacturer, same make and model receiver, tuned to the same channel, we also have to have the same encryption key to decode and analyze that signal. So if you're in a situation where security is a concern, that's a helpful feature which is available in digital systems. So that's definitely something that we want to acknowledge as well. So now we're going to get into best practices for distribution and deployment. In our next video, we're going to discuss coordination of best practices, how to set up a system day of, all of that. Here, I really just want to do a high-level overview, just in general, of what your best practices are while you're designing and setting up a system. First thing I want to point out is power and antenna distribution. Basically, each receiver, and as I showed in the earlier slides here, a receiver is a rack mount. Generally speaking, a receiver is a half-space, single-U rack device. If you're using a diversity receiver, you'll have two antenna on that. And so basically what happens is that in a single rack space now, if you have two systems, which would take up that full width of that rack, you've now got four antennas, right? As you go on and you add more and more systems, so you get into, you've got, 2 racks now. We've got 4 systems. We've got 8 antenna, right? We've got 4 spaces, 8 systems, 16 antenna, et cetera, et cetera. And so as we go up, you'll see the number of antenna that you'll be using shoots up very quickly. We see every once in a while, I didn't pull any for the presentation here. Every once in a while, you'll go onto, AV install Nightmare forum or whatever, and you'll see pictures of the back of a rack, and there's going to be just antennas on top of each other, and there's 40 antenna and that sort of thing. We don't want that. That's bad. It's not something that we want to do for a number of reasons. One, it's ugly. 2, we're creating, we set ourselves up for failure in terms of now all of those antenna can get bumped into. Now they can become loose. Why is this single channel not working? In addition to, we create RF problems for ourselves when we have a bunch of antennas in close proximity with each other. When we have transmit and receiver antennas on top of each other, we create more intermodulation effects. When we have a bunch of antennas in close proximity to each other, we run into those types of effects. We really just want to avoid that if we can. The way to fix that is by using an antenna distribution system, an antenna distributor. As you'll see on the left side of the screen here, we've got the front and back of that device. Basically with that, you'll run your BNC cables out of the antenna output of your receivers into the back of your distribution unit, and then it combines all of those into a single pair of antenna. These units are also able to be cascaded in case you've got more than 4 units in this case. This is the way that you would want to do this. The other feature that these have is they offer power distribution. Just as I had mentioned earlier, we want to cut down on the number of cables in our rack. We want to cut down on all of the extra nonsense we've got in the back of there. These are a really nice way for us to cleanly route our power without having a bunch of big IECs floating around in the back of your rack or whatever. So this is definitely something that we want to keep in mind. One of the biggest benefits to these distribution systems, as I mentioned before, is that we want fewer antennas to be used. With this, the next thing we want to talk about is how do we place our antennas? And this is one of the biggest issues that I see when I come out and I troubleshoot. I come out and I troubleshoot wireless systems, and they say, "Hey, it works really great when we're up close, but we get a bunch of people in the venue, and now we're experiencing a bunch of dropouts." The reason being, so in terms of setting up your antennas and the best placement for those, you want to have them as close to your transmit source as possible, and you want to have a direct line of sight in between them. We're going to talk about line of sight in a little bit as well, because there are certain things that even though we can see through them, RF doesn't necessarily pass through them, but we'll get there in a second. If you notice in the illustration on the right hand side of the screen here, this is something that I took from a Shure blog. There's something available on their website. It shows we've got two directional antennas placed off screen there. Just off stage there, very close to the stage, and we'll see we've got cables running to the back to front of house, where where our technician is going to be, our engineer is going to be making adjustments and all of that. What we don't want to do, and what I see very commonly when we set up wireless systems, is we'll plug the antenna directly into the back of the unit. In some cases, we'll have the wherewithal to, we can remote the antennas onto the front of the unit, but generally speaking, they live, when I see non-audio professionals set up wireless systems, we have a lot of problems with our antenna placement. And basically what ends up happening is, we end up in the back of a rack at waist height, without a direct line of sight to the transmitter. This creates a lot of problems for us in the sense that we're not able to then run and have, we're not able to have, effectively, RF likes a direct line of sight, likes to pass through clear air. It doesn't like passing through bodies. It doesn't like passing through metal. It doesn't like passing through chain link fence, that sort of thing. And so, as I mentioned earlier, we were talking about line of sight, chain link fence, for example, is not something that would allow RF to pass through. The reason being is the metal wire creates what's called a Faraday cage, which actually rejects the interference, which rejects the RF. It doesn't allow it to pass. A good example of this would be, you think of the glass door on your microwave. You've got a metal mesh over the top of it, which allows light to pass through so you can see your food cooking, but doesn't actually allow the microwaves to pass through and then cook you or everything else in the room and everything else in the room. So that's something that we want to keep in mind as well. Going back to our distribution systems, that actually allows us, these distributors allow us to do setups like what we've got in the illustration here. Basically, we have any number of systems, receivers that are in our rack there. We're able to combine everything to two, a single pair of antenna, and then place them wherever is most appropriate for us. Generally speaking, just to reiterate, best practices in terms of antenna placement are as close to the stage as possible, as close to your source as possible, direct line of sight, don't pass through bodies, don't pass through metal surfaces, don't pass through chain link fence, that sort of thing. The other thing we want to note is that the features on our stage, if this is a stage type setup, can also block our RF and block our path to our antennas. So we want to make sure that, things like drum sets, things like keyboard rigs, where there's lots of metal in them, those also will block RF. So as we do our stage design, that's definitely something that we want to think about. RF also reflects off of hard metal surfaces. So just like with audio cancellation, with multipath interactions from the loudspeaker in the room, RF can have multipath cancellations with the antenna as well. This is important to note too. When we set up our antennas, we don't want to place them, next to a hard metal table or next to if there's like a metal wall or something like that. We want to keep it away from that. The reason being is that the multipath nulls, which can be created, are almost minus 30 dB, which is a huge reduction in your audio signal, just because of poor antenna placement. So we want to make sure that we're doing everything we can to mitigate those risks. So that's another factor that we want to consider while we're determining the best placement for our antennas. There's not a one size fits all answer for this. This isn't something where we're going to be able to use this in, there's not a one size fits all solution for every event. And it's going to be, you're going to have to approach this on a case by case basis. Really what you want to end up doing is just, use your knowledge to make the best decision for your event and for your application. And that's definitely what you want to consider while you're doing this. Next, let's talk about antennas and antenna selection and what you've got. So on screen here, we've got three different types of antennas. I've got a fin here, I've got a dipole, and then I've got actually the last one is a wider band dipole as well. Basically, all of these antennas, while they do the same thing, they all operate slightly differently, and they may provide better solutions for your application depending on what you're trying to do. So generally speaking, in the center here, this dipole antenna, it's a half wave dipole antenna or quarter wavelength dipole antenna, depending on the system, is the most common antenna that you're going to see. That's generally what's included in the box when you buy a system. These are omnidirectional, meaning that they're going to broadcast your radio signal in all directions. If we're using it on a receiver side, they pick up from all directions. So if we're using on the receiver side, they pick up from all directions evenly. Important point to note, they are most sensitive where they receive the most gain is the midpoint on a transmitter, not the tip. Everybody thinks that the tip of the antenna is where the radio signal sends out from. It actually shoots out the entire length of the antenna, the midpoint of whatever frequency, that's going to be the highest RF gain. So that's something to keep in mind while you're setting these up as well. If we move to the right, the larger dipole antenna, that's just a wide bandwidth antenna. The length of the antenna generally will correspond with either a quarter wavelength or half wavelength of the frequencies that you're trying to pick up. That wider, the bigger antenna, that just is over a much wider spectrum. So if you're going to do very dense deployments where you're going across the full spectrum, I say that that's a pretty loaded statement. Where you're going to be going over using more than a handful of bands, that's the best way to do that. You're going to combine into a single system. That would be the best antenna to use. On the left side here, we've got a fin. These are directional antennas. So as I mentioned, the dipoles, the two on the right, those are omnidirectional. They send in every direction. They pick up in every direction. With the fins, those are directional. So you actually have to point it at your source. The benefit to this is that you actually get a little bit of added RF gain. Your systems become a little bit more powerful while we use this. And so if you're in a situation where, say you've got a stage set up and you've got a big LED video wall, and LED walls are awesome, they look great, but they're terrible for RF. They add a lot of noise. And you want to aim around that so that you can pick up the microphone that's front and center without any interference from the LED wall. That's where you would want to come in and use a fin, or something like that. Or you see helical antennas, which unfortunately I don't have an image of. Those are always cool. Definitely something to take a look at Google if you get a chance. Same sort of thing, much more directional, and it's much more directional. You benefit from a little bit of added gain by being directional. They also make active directional antennas, which have an amplifier in them, which you're definitely getting a lot more gain from. I'm referring to a little bit, what I'm referring to is a little bit different, but it's neither here nor there. The last point that I want to make in terms of antenna and the signal and all of that is that RF signals are polarized, which means that the transmitter and receiver antennas must be aligned to pick up the signal. So if I've got a transmitter antenna, which is straight up and down, and then I've got a receiver antenna, which is 90 degrees horizontal. So they're perpendicular to each other. Those are not polarized, and they will be out of phase with each other. So just like you think about, you've got polarized sunglasses and a screen like your cell phone, and you turn your screen 90 degrees and the screen looks black through your sunglasses. Exact same concept here with your antenna. Because they're polarized, if you go 90 degrees out of orientation, they'll cancel out. Generally speaking, your polarity nulls are going to be about minus 10 to 12 dB. So just to put this into perspective here, yes, losing 10 dB or 12 dB of signal is huge. You're definitely going to notice that you're going to create problems. The nulls from your multipath, which I had talked about in terms of antenna placement, and the surfaces around it, are minus 30. So multipath reflections can create bigger problems, create more headaches for you than polarity. Now, with all of that being said, we do have the option for, with all of that being said, there are antennas, helical antennas, for example, are not polarized. So if that's something where you've got a performer who's moving around a lot, and orientation may be a concern, that is, a better option for you. So there's always options to work with. And so that's all I've got for today. I truly appreciate you taking the time to watch this video. I really hope that you found it informative. In our next video, as I mentioned, I'm going to be going over how I use RF Explorer and Shure Wireless Workbench to conduct an RF coordination and deployment for systems when I get on site. So that's definitely something to look out for. I hope you guys will find that informative as well. If you guys have any questions or concerns in the meantime, please feel free to reach out to me at nick@redlabelproductions.com, or reach out to Red Label if you have any wireless or rental or deployment needs. And so with that, we hope you guys have a great day, and we'll be in touch soon.